We've spent the last few class periods exploring the properties of exponents, really so that we could gear up and talk about what are called exponential functions. So these are an entirely new set of functions. We spent the entire fall talking about linear functions, which are like, straight lines. But now we're going to be talking about exponential functions, which are just equations that are non-linear and are exponential. Okay, so this is a whole new, brand new type of function. Now you have two examples of what most exponential functions look like. There are two other options that we're not really going to go into detail right about now. Now some things I want you to notice about these graphs, okay, the red lines right here, they're called curves. So we're no longer going to call them lines, we're going to call them curves because obviously they're curves. There's a couple important points to note. You need to notice that they cross the y-axis just like our linear equations do. That is still called my y-intercept. But one of the things we're going to be talking about with these exponential functions is whether they are called increasing, like this one that goes up, increasing, or decreasing functions. Now, exponential functions model some really cool things out in the universe. They model bacterial growth, decay of bodies for like forensic scientists. It's all about money and bank accounts and how it grows and how you might owe a lot of interest rates on different credit cards or something like that. So understanding the basics of these exponential functions is actually pretty important for your adult life. Okay, you have the basic exponential function right here. Don't highlight it on your paper, but I just wanted to call attention to it. Okay, that right there is the basic exponential function. It is like the y equals mx plus b for exponential functions, but it is called f of x equal to a times b to the x power. One of the things I want you to notice is that x is an exponent. This is why it's called an exponential function. Okay, like the m and the b are particular in y equals mx plus b, the a and the b here are also particular. The a, or the first number in this formula, is the initial amount. And we know that through studying linear equations, the initial amount is my y-intercept. So the number that is right here in front of the parentheses is going to be my initial amount, or where that graph crosses the y-axis. The b, or the base, b for base, in exponential functions is called my constant ratio because it's the ratio with which the numbers are changing. So if it says my function is doubling, double is 2, so my constant ratio would be 2. This would be an increasing exponential function. So a equals b to the x is how you say the parent function or the basic formula for an exponential function. Now there is some new vocabulary or reviewed vocabulary when we talk about exponentials, so we need to go over that for a little bit. We did just define the initial amount. Remember, the initial amount is your y-intercept. It's where the graph crosses the y-axis. And for an exponential equation, it's going to be the coordinate point 0, a. That's going to be the initial amount that a word problem tells you, or the initial amount that begins your problem. The constant ratio, again, is your b value. But this is how the function changes, okay? So this is what we're going to multiply by each time we plot a new point. It's our constant ratio. So again, if I say it doubles, we're going to multiply by 2. If I say it triples, it's going to multiply by 3. If I say it halves every time, you're going to multiply by a half. The constant ratio. Now the last word on here is definitely a new vocabulary word for you, and I will totally be cool if you giggle for a hot second on this word, but this is pronounced horizontal asymptote. A horizontal asymptote will always be drawn on a graph with a dashed line because it's not really there. It's an invisible line that we know is there. It's like a boundary, so an invisible line or boundary that the graph approaches but never touches. For exponential equations that we learn about in this class, the horizontal asymptote is pretty much always going to be y equals 0, which is your x-axis. Okay, so if I ask you for the equation of the horizontal asymptote, you're going to say y equals 0. Now we're going to have to talk a little bit about what a horizontal asymptote looks like and why it is an invisible boundary line that the graph approaches but never touches. So I'm going to zoom in up here on these two graphs from the beginning to kind of draw it in and show you what I'm talking about. Okay, so because I'm a human and I'm drawing on top of a screen and you're going to be drawing on a piece of paper, your line for your horizontal asymptote will essentially look like it touches. But if we were computers or we zoomed in on Desmos very, very close to the x-axis, you would see that this red line is actually never going to cross that horizontal asymptote. It's like an invisible line that the graph never touches. It is a very important boundary line for these kind of functions. Okay, so the horizontal asymptote is right there along the x-axis for these types of functions. Again, it doesn't actually touch this line, even though like I'm a bad drawer and it does totally touch the line. Okay, does not touch the curve. It is just this line down here, the x-axis. Now, some of the things we're going to need to know about exponential functions, since we're defining an entirely new function, is we're going to have to know its properties, like its y-intercept or initial value. We're also going to have to spend some time talking about its domain and range. Okay, so quick review of domain and range. Remember, just some things to remember about domain and range, that if you have a closed-in circle, or the graph exists there, you're going to use the less than or equal to symbol in your domain and range. If you have an open circle or an arrow, you're going to use just the less than symbol in your domain and range. We also know that from Dolor the robot, when we talk about domain, we're talking about the graph, describing it from the left to the right of the graph. So as far left as it extends to as far right as it extends. And for the range, we're talking about this graph from the bottom of the graph to the top. So from its lowest to its highest points. We also know that for domain and range, we can use this pattern that's found on your formula chart in supplemental aid to describe the graph from the left to the right and to describe the graph from the bottom to the top. You just have to pick the symbols and the numbers that go each place. So if I look at number 1, it's asking me to describe the domain and range of the function. I first noticed that we have two really good endpoints here and here. Great. That means I'm just going to describe basically where this graph shows up by boxing it in. So here we go. We have the very left of the graph here and the very right of the graph there. It does not extend any more left or any more right than what I've already put down on this paper. So what we're going to do is we're just going to pick up those numbers and describe them from the left of the graph with a closed circle to the right of the graph with a closed circle. This is saying that this graph shows up on the x-axis between 1 and 3, which it totally does. If I go to do my range, again, I'm looking for the lowest point of the graph to the highest point of the graph. I can say this is approximately 6 with a closed circle, all the way up to 27 with a closed circle, saying that this graph shows up on the y-axis from here to here, which it does. We've talked about domain and range before, so this should really be a review of the concepts of domain and range, just with a new type of function, a curve, an exponential function. Now we get into some really cool ones here. On number 2, it says to describe the domain and range again. But if I look at this graph, I would notice that there is an extension, an arrow extending off the graph on both the left and the right, which means this graph is going to continue going all the way to the left and all the way to the right. So when I go to do my domain, the very left of the graph would be continued on and on and on. So this is going to be negative infinity all the way to the left. And on the right, it's going to continue that way as well, all the way to positive infinity. Now, when we have double infinities on our domain and range, this actually is called all real numbers. Okay, or you can write down the fun and funky R, which I will probably be doing. When we go to do our range, though, with exponential functions, on the front of this packet, we talked about a line right here. What was that line called that's an invisible boundary? Yeah, it's called the horizontal asymptote. And I said that that curve is never going to cross the horizontal asymptote, which means I know I have a lower boundary here at 0 that y is never going to touch. okay? Never touches it. So 0 is the lowest it's going to go. But if you look up at the top of the graph, it's got an infinity sign up there because the arrow is going to keep going up and up. So to actually write this, or what you would see on answer choices for tests, because we don't include the infinity signs in our domain and range, is just y greater than 0. So 0 is less than y is the same thing as y greater than 0. Cool. Now the only way I can make this more confusing is if I put a real world scenario on it. Now this is the main reason we do domain and range. We want to know what's reasonable for our inputs and outputs when we're actually studying something with math. Number 3 has a bacterial population, a certain number of days, and how much it grows. Okay, here's a couple things we notice. We notice that the very, very first day right here, day 0, we have 3 bacteria in our population. We also notice that we have an arrow continuing on and on in one direction. So if I was doing my domain, that's looking at the x's. Here's my first x, which is 0. So I know my graph is at least going to be bigger than or equal to 0. And then on the right, I see it's going to keep going to infinity because this bacteria can keep growing. So my domain is x greater than or equal to 0. For the range, I see that my very, very first range where this graph starts is 3. So that's going to be my first number included in my range with a closed dot. But I also see that this graph is going to keep continuing up, so it doesn't really have a top. It has an infinite top number. And so my range is going to be y greater than or equal to 3. Fantastic. So we've reviewed domain and range before. We spent a lot of time on that when we learned about it with linear functions. So we're just applying those ideas of inputs and outputs, left, right, bottom, top, to exponential functions. Last thing we want to do here is graph the functions. These are very easy to graph when I'm picking nice, pretty numbers for you. We're going to start by graphing the initial amount and then use the constant ratio to create more coordinate points. So for number 4, it says f of x is equal to 8 times 1/2 to the x power. Well, I know that my initial value is that first number right there. My initial amount is going to be 8. So I can go ahead and plot me a little point at 8. That's going to be my initial value. My constant ratio is the number in the parentheses, or the number with the x attached to it, which is 1/2. That means to create more points, all I'm going to do is take 1/2 of 8. Well, that's 4. Then 1/2 of 4. Well, that's 2. 1/2 of 2. Well, that's 1. And 1/2 of 1 is 1/2. After that, it gets crazy small, so I'm not going to do that. But I'm also going to work the other way and double 8 to get 16 for -1. At this point, I would be able to very sloppily, because y'all know I can't draw anything, draw a nice curve, yikes, on this graph. One thing I want you to notice that I did on purpose is that I did not cross this horizontal asymptote with my line, because I know that this graph has an asymptote at y equals 0 that it cannot cross. If we again do its domain and range, I notice that I have arrows on both sides, so this graph is going to keep continuing on to the left to negative infinity and on the right to positive infinity, which means that the domain here is all real numbers. It's going to keep going both directions. I've never told you where it stops. But its range, remember, since it can't touch 0, is going to have to be above 0 and then all the way up to infinity. So my range is going to be y greater than 0. Now, if the domain and range part of this is still confusing you, don't worry, we'll work it out in class, but I want to make sure you understand the A and the B when we're graphing. So on number 5, I would like for you to graph this one for me. Before I let you go, though, I want to help you find the different numbers. Now, we said that the constant ratio is the number in parentheses or the number with the x attached to it. So the constant ratio is going to be 2. We're doubling numbers here. But there's like not a number here. What number is hidden right there that mathematicians don't write all the time? Yeah, there's a 1 right there. So my initial amount is going to be 1, and my constant ratio is going to be 2. Pause the video right now, see if you can graph a few coordinate points to create this curve. Feel free to make fun of my curve and how wobbly it is, but here is what I did. You have an initial value of 1 and a constant ratio of 2, which means I double that every time. If I double 1, that's 2. If I double 2, that's 4. If I double 4, that's 8. Doubled is 16. And that creates my curve here, my exponential curve. Hopefully you did this thing down here where you didn't actually cross the y-axis, because we know that this graph has an asymptote at y equals 0. Again, because the domain extends from negative infinity to on the left to infinity on the right, my domain is going to be all real numbers. And my range is going to be all the y's greater than 0, since it has that horizontal asymptote here at 0 and extends forever and ever up to infinity at the top. So we introduced a whole new type of function today, an exponential function. We're going to be focusing on its domain and range and then graphing the function in class. So let's make sure that we fully grasp the idea of domain and range, left, right, bottom, top, and the initial amount constant ratio. That really makes sense from what we already know about y-intercepts and what we can kind of infer from what we know from exponent rules. Again, if you're going to remember one thing from today's lesson, I would love for you to focus on the function itself and the shape of the curve. See y'all in class.